Hi everyone, welcome back. So now I'm going to talk about, I'm going to give two examples on how to compute lift coefficient for cambered airfoils. So the first problem is, if you can open up your slide, it should be slide number 23, page number 23. So the problem is, consider an airfoil that has a camber line, ZCX at epsilon is the expression of epsilon 1 over 2c times x squared plus epsilon 2 over 3c squared times x cubic. And now, how can we actually get the, let's say, the lift coefficient as a function of alpha, epsilon 1, and epsilon 2. Okay, so right now you can think about epsilon 1 and epsilon 2 as sort of design parameters. So if you want to design a certain specific lift coefficient, then maybe you can tune this epsilon 1 or epsilon 2 to achieve some sort of desired performance that you want. Okay, so the first thing we do in order to solve this problem, so answering this problem, the first thing we do is we compute the derivative of the center line. So basically we get the slope of the, the camber line, sorry. Okay, so we just need to compute this one, dz(x) respect to x, okay, over dx. So this expression is going to be basically epsilon 1 divided by, just use black colors, epsilon 1 divided by 2c x squared plus epsilon 2 divided by 3c squared x cubic derivative of that would just becomes epsilon 1 x over c plus epsilon 2 x over c squared. Okay, that's the slope for the camber line. Now let's replace the x with theta. That's the second step. So now the relation, of course, is x equals to c over 2 1 minus cosine theta. Theta is, of course, from 0 to pi, and x from 0 to c. Okay, so now we have these derivatives as a function of theta. Actually, right now it's become a function of theta, and the expression would be epsilon 1 divided by 2 times 1 minus cosine theta plus epsilon 2 divided by 4 1 minus cosine theta squared. So this is the result. If we kind of divide it, you replace x with theta. Okay, so if I kind of expand this term, that's going to be epsilon 1 over 2 plus epsilon 2 over 4 plus minus epsilon 1 over 2 minus epsilon 2 over 2 cosine theta plus epsilon 2 over 4 cosine theta squared. Good. So next, once we get the slope, I'm going to kind of arrange it a little bit. So because we have a cosine theta squared, I'm going to rearrange it. Recall that cosine theta squared minus 1 is cosine 2 theta. Therefore, we can actually rewrite this expression as theta 1 over 2 plus 3 theta 2 over 8 minus theta 1 plus theta 2 over 2 cosine theta plus theta 2 over 8 cosine 2 theta. Okay, this is just the same expression as before, but I just used some relation to sort of simplify it a little bit. Okay, because later on we will use orthogonality of cosine series. So making all the square of cosine goes away will be a wise choice. Okay, Next thing, the third thing I'm gonna do is I'm just gonna compare this. I'm gonna try to compute. So the third thing I'm gonna do is basically I'm gonna just trying to come up find the A0 to A0. This is what I'm gonna do. And actually, for this problem here, it's actually pretty simple. Remember that we have this equation, the slope equals to alpha minus A0 plus a trigonometric relationship, okay, of cosine and theta. So now we want to find A0 and AN. But if you look at this problem here, you know, it looks like I can just figure out A0 and AN just by bare eyes, right? So, right, basically the constant term corresponding to the alpha minus A0, and the first cosine theta term corresponding to A1, and the cosine 2 theta term corresponding to A2. Therefore, alpha minus A0 is epsilon 1 divided by 2 plus 3 epsilon 2 over 8. And A1 equals to minus epsilon 1 plus epsilon 2 divided by 2. Okay. And epsilon 2 is epsilon 2, A2 is epsilon 2 divided by 8. Great. So we have the A1, A2, and anything sort of larger than, for anything that's larger than 3, is for the n larger than 3, an is going to be 0. Great. Therefore, you just need to plug in our previous formula for the lift coefficient, which is going to be 2 pi A0 plus 1 over 2 A1. That would be A2 going to be A0 basically going to be alpha minus this thing, and A1 is basically this thing. So we just arrange a little bit. We get 2 pi times alpha minus 3 epsilon 1 over 4 plus 5 epsilon 2 over 8. Great. So this is what we got. It's the expression. We have the lift coefficient as a function of not just angle of attack, but also the shape parameters of the airfoil, epsilon 1, epsilon 2. Okay, good. So for the second question, it's actually pretty similar. The problem 2, it's pretty similar, except you need to just do a little bit more computations. So the problem 2 is we have these sort of slope for sort of the shape for the airfoils is just like piecewise linear shape. Okay, and sort of for each piece there is a different slope. For this one, I think it's here's 0, and this one is c over 4. Here is c over 2, and here is 3 over 4, and here is c. So I have d1, d2, d3. Okay, so that's all we need to actually figure out. And this is all we need to actually describe the sort of the piece